The epsilon-delta definition you learned in calculus is only level 2 of a 6-level hierarchy. Look at these 6 ascending tiers, epsilon-delta at level 2, highlighted here in green. Each level was invented to fix a logical gap in the one that came before it. At the very top, limits detach completely from numbers and from distance. Left, rulers and number lines. Right, no axes, no measuring tape, just abstract structure. The same notion of getting arbitrarily close now works in any space you can define, from ancient paradoxes to modern topology. This is the full hierarchy of limits. Let us begin at level 1. Can you ever finish walking across a room? This is Zeno's paradox. You must walk half, then half of what remains, then half again. Infinite steps. Watch the walker. Each step halves the gap to the wall. The distance shrinks towards 0 but never reaches it. This felt like a contradiction for 2,000 years. The first rigorous definition of a limit finally resolved it. The limit of a sequence, an ordered list of numbers that gets arbitrarily close to a target value L. Here is how the formal epsilon-n definition works. Plot the terms against the index n. The yellow line is the limit L. Pick any tiny epsilon. The green band is the epsilon corridor around L. Some step n always exists. After n, every remaining term stays inside the epsilon corridor and stays there forever. Shrink epsilon, n moves right, but it always exists. No infinitesimals, no hand-waving, just numbers and an explicit guarantee. This handles compound interest, infinite series, population growth. Zeno's walker does cross the room. The infinite sum of halves converges to 1. Cauchy formalized this definition in the 1820s, putting limits on solid logical ground for the first time in history. But this definition only works for discrete, step-by-step lists. The real world is continuous, moving objects, flowing fluids, smooth curves. A definition built for whole number steps cannot describe what happens at every point along a curve. To fix that, limits had to be rebuilt for continuous functions. Newton and Leibniz invented calculus using infinitesimals, quantities so small they were treated as 0. The calculations worked, but the logic was shaky. In 1734, George Berkeley attacked. Look at this horizontal segment labeled dx on the curve. Watch what happens when we examine it closely. It collapses towards 0. Is dx 0 or not? If it is 0, you cannot divide by it. If it is not 0, your derivative is only approximate, a contradiction. Berkeley called it a ghost of a departed quantity. Calculus worked, but its logical foundation was rotten. The repair took over 100 years. Here is the solution. Pick any vertical epsilon around the limit L. The green band is the epsilon tube. Now find a horizontal delta window around the input point C. Wherever x sits inside the orange delta window, the output f of x stays inside the green epsilon tube. Input within delta implies output within epsilon. Watch the green segment of the curve. It lives entirely inside the epsilon corridor. Shrink epsilon. The delta window narrows to match. For every epsilon, a delta exists. No infinitesimals, no ghosts, just ordinary numbers and explicit error bounds. Berkeley's paradox is completely resolved. This defines continuity, derivatives, integrals. Everything in real analysis traces back to epsilon and delta. Weierstrass finalized this in the 1850s. It became the undisputed backbone of calculus. Physics, engineering, economics, all of it rests here. But it has a hidden limitation. Both epsilon and delta are finite numbers. The definition only works when input and output are both finite. What if a function blows up to infinity near a point? The finite framework has no language for unbounded behavior. To give infinity a rigorous meaning within limits, mathematicians had to stretch the definition yet again. 2 elegant extensions that transform infinity from a vague gesture into a precise tool. For a long time, saying the limit is infinity was considered sloppy. Infinity is not a number, so how can you approach it? But real problems do not care. Light intensity near a source blows up. Escape velocity tends to infinity. Growth rates rise without bound. These three curves all shoot off the chart. The old epsilon-delta cannot describe this. So mathematicians gave us two essential extensions. First, limits at infinity. Instead of approaching a finite point, we let x march to the right forever. What happens to f of x in the long run? Watch the blue dot. As x grows, the curve flattens onto this yellow horizontal asymptote. The gap shrinks, getting arbitrarily close without ever touching. The target C has been replaced by infinity itself. This unlocks long-term behavior, saturation, steady states. Where does this system end up if I wait long enough? Limits at infinity answer that question. Second extension, the mirror image. Approach a finite point, and the output blows up without bound. Watch the orange curve. There is a vertical asymptote at x equals 0. As x gets close to 0, the function shoots upward, racing toward infinity. Draw any horizontal threshold, m. The function crosses it. Draw a higher m. It crosses that too. The function exceeds every bound you can name. The limit is no longer a value. It is the statement that the function grows without bound. Both extensions share the same core idea. This unlocks asymptotic analysis, big O notation in computer science, orbital mechanics, long-term predictions of dynamic systems. But even these extended definitions have a blind spot. Everything so far assumes exactly one input variable. The moment you move to 2 or 3 dimensions, something deeply counterintuitive happens. Approaching a point is no longer a simple left or right decision. One innocent function of 2 variables broke the naive O-dimensional intuition. When mathematicians extended calculus to 3 dimensions, they assumed limits would work just like in 1 dimension. They were wrong. This innocent function changed everything. F of x comma y equals xy divided by x squared plus y squared. We want the limit as both variables approach 0. First, approach along the axis where y equals 0. The green dots move in. The function is identically 0 all the way. The limit along this path, 0. Now approach along the line y equals x. Watch the purple dots. The function equals 1/2 everywhere except at the origin itself. The limit along this path, 1/2. Same point, the origin. 2 paths, 2 different answers, 0 and 1/2. A contradiction. The limit does not exist. This single function broke the naive y-dimensional intuition that all roads lead to the same destination. The fix is simple and demanding. For a multivariable limit to exist, every possible path must give the same answer. Not just straight lines, not just curves. Every single path. Look at this top-down view. Here is the target point, a green line, a blue parabola, a purple spiral, an orange diagonal. 4 different approaches, all converging to the same point. If the function gives the same limit along these 4, you are not done. You must prove it for every possible path, including ones you cannot easily draw. Epsilon-delta now measured by distance and dimensional space. Same logic, higher dimension, one differing path, and the limit collapses. This is the gateway to vector calculus, partial derivatives, fluid dynamics, electromagnetism. It extends rigorous calculus to the 3-dimensional world we inhabit. But there is a different limitation. Epsilon-delta, even in n dimensions, assumes sequences eventually settle down. What about sequences that refuse? Think of 1, -1. 1, -1, repeating forever. It bounces. It never converges. Yet it is bounded. It stays between -1 and 1. To capture the boundaries of oscillating behavior, mathematicians invented limit superior and limit inferior. 2 rails. The sequence can never permanently escape. Consider the simplest oscillating sequence. 1, -1, 1, -1, repeating forever. By the standard definition, no limit exists. For most of mathematical history, that was the end of the story. No limit, nothing more to say. But look again. The sequence is clearly bounded, or with the never exceeds 1, never drops below -1. There is structure here, even without convergence. The tools that capture this are limit superior and limit inferior. Watch as two dashed lines appear. The orange line at the top is lim sup, the least upper bound of all the tail ends, the smallest ceiling the sequence will never permanently exceed. The deep blue line at the bottom is lim n, the greatest lower bound, the largest floor the sequence will never permanently fall below. The purple corridor is where the sequence lives. For any bounded sequence, lim sup and lim imp always exist, even when the ordinary limit does not. They extract information from non-convergent behavior. But watch what happens when the sequence actually does converge. Here is a damped oscillation that settles towards zero. The dashed envelopes appear. The orange upper envelope traces the decaying peaks. The blue lower envelope traces the troughs. The two rails squeeze together. As the oscillation damps out, the envelopes pinch toward each other. When they finally meet, when lim sup equals lim inf, that common value is precisely the ordinary limit. The yellow marker shows the meeting point at 0. Lim sup equals lim imp equals the ordinary limit. The standard definition is just the special case where the two rails coincide. Lim sup and lim generalize the ordinary limit. Convergence means they agree. Oscillation means they bound the behavior. These tools are foundational to 20th century real analysis, convergence tests for infinite series, analysis of random processes, Fatu's lemma in measure theory. But here is the flaw. The entire framework depends on order, on one number being greater than another. Strip away the ordering of the real numbers, and lim sup and lim im become meaningless. What if your mathematical space has no ruler, no number line, no concept of greater than? To define limits in the most general setting imaginable, you must abandon almost everything. By the early 20th century, mathematicians were studying spaces with no numbers or geometry, spaces of functions, spaces of sets, pure abstract topology. Look at this number line. Every limit definition we have built depends on this structure. A ruler, a way to measure distance, but in a space of functions, there is no number line, no distance formula. The red strike says it all. No distance. All our previous definitions fail. The question, what is the absolute core of a limit? The answer, nets and filters. Two equivalent forms of the same idea. A limit is about eventually staying inside every neighborhood. Look at these shapes, not circles with a fixed radius. Abstract sets, blobs that nest inside each other, shrinking toward a central point. No numbers label their size. A point approaches a limit if, for every neighborhood, the point eventually enters it and stays inside. The blue dot falls into each successive ring. No epsilon, no delta, no numbers at all, just the notion of a neighborhood and the guarantee of eventual entry. A net generalizes a sequence. A filter describes limit behavior using collections of sets. Both preserve uniqueness of convergence. Now contrast the two worlds. Left, levels 1 through 5, approach by distance, measure the gap. This is the world of numbers and rulers. Right, level 6, approach by sets, eventually inside every neighborhood, no measuring tape, just abstract containment. That equal sign tells the deepest truth. These two pictures describe the same logical idea. Filters strip the limit to its purest essence. And now the deepest fact of the entire hierarchy. Every lower level is just a special case of filter convergence. Sequences, epsilon-delta functions, infinity limits, multivariable limits, lim sup and lim inf, all 5 feed into this one unifying node, filter convergence.